Morning. Welcome to this start of this deep dive fortnight in energy within the programme on foundation, data and engineering. And one thing I'd like to do first of all is thank the organisers of the overall programme for the opportunity to come together with energy. We will start off with introductory talk today to motivate three thematic areas which we think are ones where we can make good progress during the fortnight. This isn't exclusive period of these three topics. So if people want to talk about other things, that's absolutely fine. I'd also like to welcome the people that we've invited especially for this fortnight, and also welcome the people who are longer stayers on the programme. One of the exciting things is bringing the energy specialists together to work on some of these important scientific societal challenges, but also it's very exciting to see what happens that we couldn't have predicted. And one remarkable thing that the Movement Chief does, which I'm not quite sure this is something one would invent if one's already here, is that it does bring people together for extended periods simply to make progress on these kinds of questions without asking anything very specific of us. And past experience shows this is actually extremely effective to bring people together and give them space. After this, we don't have any particular structure. We're simply able to come together and discuss. We'll range a few talks, including a couple of interesting presentations probably next week by people who were invited but couldn't make it to Cambridge. And there's always the opportunity if anyone wants to give a talk or schedule a discussion session on a particular topic, we can do that on a daily basis. I'd like at the end of it to have some kind of record of what it is that we've done. So we need to, both this will be helpful for justifying ourselves to anyone, but also I think importantly, where we have made progress on questions, it's very helpful to be able to report this to other than research community, but also particularly to anyone in industry or government who might find what we want helpful. So we want to do some good science, but we also want to lead things happening out there in the world. So the day is divided into three sessions according to these three themes. First is on decision support for complex systems. And probably of the three themes, this is one where I think a lot of big challenges are not so much energy specific, but simply when you have the techno-economic, societal, environmental, whatever you call it, systems, which are far more complex than any model could possibly be. When we get started on questions of decision support, so very pleased we've got two speakers. First is Mark Enzer, who I met through work on the National Digital Twin Programme, which he led, and who comes at these questions of modelling and data for very complex systems from a senior perspective in industry. Then Jim Smith, who works in research from an efficient analysis perspective, and who's also been part with Mark and myself with National Digital Twin Programme work. The plan is for this that we'll run the few talks, and then we'll have a joint question and answer discussion with Jim and Mark, and then we can head to lunch. I should add that the talks being streamed for the benefit of some people in the programme who probably hear it every day, also recorded for the benefit of people on the programme. We can decide afterwards whether we want any of the talks to become part of the Movement Chief archive. I mean, my guess is by the nature of them, it's natural that some of and for others, there'll be more informed discussions in makes sense to archive and brought explore the expression too. And so I should also give a warm welcome to those elsewhere in the country or the world. Obviously, I'm assuming for John Paul Watson, who couldn't make it, is not watching live from California. And I'm very pleased to hand over to Mott to speak about infrastructure systems and digital twins.
Thank you very much. Good morning. It's really nice to be here. I should probably declare right at the beginning that I'm an engineer, not a mathematician, so forgive me because I'll probably say all the wrong things in the wrong order. But I think mainly what I intend to do is lay some context, and hopefully that context will be useful for your ongoing discussions in this deep dive around energy, but also hopefully spur some thoughts when it comes to this idea of decision support for complex systems. So I'd like to describe a particular set of complex systems which are to do with the built environment. So that is my background, it's a built environment. As Chris mentioned, I've been working on the National Digital Twin Programme. I was the head of the National Digital Twin Programme at the Centre for Digital Britain, which is based here at Cambridge University. That has now come to an end, the funding for that finished. I'm still heavily involved in digital twins and still very, very much interested in this space. And the issues that we will be discussing and I'll be raising are super current. You know, these are really important things which we need to get answers to. And even get to the point of being able to ask the right questions. You know, this is I think quite early stage, and therefore this is very helpful indeed, just to kind of get some brains together and to think about it. So when it comes to setting this context and kind of getting into it a bit, what I thought I'd do is really two things. The first is lay some very broad context about infrastructure systems in general. So starting at the kind of the widest possible view, and then come in and talk more specifically about digital twins, introduce what they are, the idea of connected digital twins, and then try and make some kind of connection between those two subjects, how we might use digital twins to make better decisions faster, how we might use connected digital twins to understand systems better and intervene more effectively. But there's no point of doing that unless we understand what the whole system is for in the first place. So that's why I intend to do it in that way round. And maybe I should also say that while we were working on the National Digital Twin Programme and very much focused on the built environment, we found that everything that we were uncovering was highly relevant in other sectors as well. So even though I might use all my examples from the built environment, I think that this very same thing is relevant in healthcare, it's relevant in education, it's relevant in defence, advanced manufacturing, etc. Okay, so starting with the broadest possible context, kind of the reason why, what's all of this for, what's the driving purpose. We got this whole thing of the planet burning, which to me feels like a pretty big reason to get up and do something. I hope that all of us here are convinced that climate change is a real thing. Humans got a big part in it. And that affects all of our systems, every single system that we rely on, our built systems, but also our natural systems. So we've got a pretty big kind of forcing function here, a reason to get on and do something. And part of the reason for me to show the burning Earth, other than to wake us all up, and it's a nice slide, is to say that our infrastructure systems are facing really big systemic challenges. Climate change is clearly one of those, but if we're going to address climate resilience or achieve net zero or achieve a circular economy or address the relationship between biodiversity and our built systems or provide infrastructure equity, I could go on. All of these things are system level challenges that cannot be solved in silos. They demand systems-based solutions. So really, it's about time that we got our head around the system challenges, and how we can basically understand the systems better and intervene more effectively. And that's probably a phrase that I'll use maybe 5 times in this talk. So if we're starting from that very big picture of the reason why, I think it becomes important to see the built environment in that context. And I think, therefore, it's useful to see the built environment as having a purpose, rather than just being a thing that is there, or the result of a lot of construction projects, to actually see that the built environment itself has a purpose, to recognize that purpose, and then to try and achieve that purpose. And I would put it that the purpose of the built environment should be to enable people and nature to flourish together for generations. So packed into that little phrase is quite a lot of stuff. It's not just about people, it's about nature as well. It's about flourishing. So that's not just about money measured wealth, but a broader measure of wealth, people and nature flourishing. And for generations. So not just for now, but for all the generations, because basically anything we do in the built environment lasts for an awful long time. So if we have this, if we buy into this, because I know it's a perspective, it's not the only way of seeing things, but if we buy into this, it's kind of saying the purpose matters. That's another word you're going to hear me use a lot. So let's understand the purpose of the built environment. Once we've got a purpose, let's work out how we achieve that purpose. And in doing that, I think it's incredibly important to see the built environment itself as a system of systems. So it's not just an individual system, it's an amazing, complex interaction of multiple systems. So if we start with economic infrastructure, in the UK, that's defined as being energy, transport, water, waste, telecoms. Each one of those is a complex, interconnected system, but each one depends on the other. So increasingly, transport doesn't work unless energy is working. Energy doesn't work unless telecoms is working. In fact, none of them work if water doesn't work. We all need water to work. It's one of the most fundamental ones. But water then depends on energy and telecoms as well. So you get the picture. Every single layer of economic infrastructure is essential and connected to the other layers. Interesting to note as we go past that each one is managed in a silo. So even though our systems are connected, the way we manage them is less connected. But that's not the end of the story, clearly, because we also have our social infrastructure. So that would be our hospitals, our prisons, our schools, commercial, residential, industrial buildings. And basically, none of those work, none of those make any kind of sense unless they're served by the economic infrastructure that kind of connects them all up, provides utilities for them. And then that's still not the end of the story, because we have the interface with the natural environment. The natural environment itself, clearly complex, interconnected system of systems, but the way that the built environment interacts with the natural environment is incredibly interesting and important. You know, just think about flood prevention as a simple example of that. So if you take each of those layers, which themselves are amazing and complex and interconnected, you stick them all together, you end up with the built environment. You know, this amazing, complex organism that we live inside, that we depend on. If it weren't there, then you know, we wouldn't survive. Society wouldn't work. But we hardly notice it. It's one of those things that it's so important and so kind of all-encompassing that it's hiding in plain sight, and therefore quite often we don't pay it the attention that it deserves. But this is the built environment that I'm talking about when I'm talking about the purpose to enable people and nature to flourish together for generations. Okay, so I think whereas what I said before was just an opinion about, I think the built environment should have a purpose. I think that the built environment being a system of systems is a fact. It is. That's just what it is. Just describing it. And being a complex system of systems, it also has a number of other things which go with that kind of complexity. So it's actually an adaptive system. You kind of push it in one way and it will react and kind of move in another. And there are all sorts of emergent properties coming from that system too. So it's got an awful lot of the characteristics of a very interesting and exciting system of systems. And part of that means that it cannot be controlled. So one of the wonderful things about engineered systems is that they can be controlled. And that's what a lot of engineers like. You design a system so that you can control it and it's controllable, and that's nice. But then when you add that controllable system to another one, and then another one, and another one, and you end up with this complex system of systems, it stops being controllable. So I think it's one of the most important things to kind of point out here is that this overall system of systems cannot be controlled, but it can be understood. I think that one of the key things we therefore need to do is understand it better to enable us to intervene more effectively. And if we zoom in on this complex system of systems, the built environment, we see that there are a whole load of processes that go on within the systems, which are really important. I would suggest that the most important of those is use. It's the use of the systems. That's where we get the utility. That's the value of it. And if we're going for circular economy, for example, then what we need to do is maintain it at its maximum value of use. So the use is at the center. But then in order to make the built environment available for use, we need to operate and maintain it properly. And these are system processes. They have to go on forever. They don't have a life cycle. And the system itself doesn't have a life cycle. It's like Trigger's broom, if you're familiar with that, or my grandfather's axe. Remember, Trigger asked how old his broom is. He said he's had the same broom for 15 years. It's had 5 heads and 3 handles, but to him, it's the same broom. It's the same thing with this system of systems. You keep on adding bits, taking bits away, but it's the same system. So operate, maintain, and use are system processes that have to go on forever. But then every now and again, we add in some life cycle processes, which are about managing assets. So we might need a new asset. So we plan, design, construct, and build, and then integrate that asset into the system. But I think it's really important to see that it's a system, it's about the system. More often than not, the construction industry thinks that the built environment is a series of construction projects. It's not. It's a system of systems. Construction projects are interventions on the system. So when I said earlier on that I think what's important here is that we understand the system better and intervene more effectively. Those interventions are incredibly important because those interventions are adding new assets or modifying what we already have. But the interventions are not the important thing. The important thing is the system and the use of it. If that's okay. But there's a big question as to whether or not those interventions are the right ones. Are we building the right project? Are we doing what is necessary to get the most out of that system? At the moment, we don't either ask those questions very well or answer them. Generally, what happens is that we just go and do some more projects. And if we think we need something, we build something rather than look at the system and understand its needs to get the best outcomes. And so what I would suggest here, as an overall model, is that we should be entirely focused on the outcomes, and that in order to get the best outcomes, we should understand the system better and then intervene more effectively. I did say I'd say it all the time. And this I think, is a kind of a basic model of that, seeing how we get to those outcomes from the interventions. So here on the right-hand side, we've got a whole bunch of nested outcomes at the highest level. The Sustainable Development Goals, kind of a global thing that we all think is a really good thing to do. But those need to be aligned all the way down to local outcomes from local projects. So the local project needs to be part of doing something that actually helps to deliver the SDGs. If local projects don't do that, they're probably the wrong project. So there's this alignment of outcomes from local to global. But then how do we get the outcomes? I've suggested that it really comes from the use of the systems, which are services. And so that means we don't really want a bridge. What we want is mobility, and the bridge is just part of delivering that mobility. And what we want is shelter. So the built environment provides these essential services, but so does the natural systems provide essential services. So the air we breathe, the water we drink, etc. So the services we get from these systems becomes really important. And that's why it's so important to understand the systems better. And then within the built systems, we have these processes. Within the processes is where the decisions sit. And if we want to manage those systems better, we have to make those decisions better. Better decisions faster will lead to better outcomes. And so this is kind of the essence of what I like to say. I rarely get the opportunity to say it, because normally if I'm talking about this stuff on a stage, I can't get to this level of just talking about the stuff I want to talk about. I need to kind of talk about projects and examples and blah, blah, blah. But I think that this is the essence for me. It's about making better decisions within those processes to enable the systems to work better, to get better use in order to enable the better outcomes. But it's really outcomes focused and it's systems based. Okay, that was my context. That was the context for the built environment and where I think everything we're considering sits. Now I was going to do digital twins and do it relatively quickly. And I'm starting with a bit of a noddy example, so forgive me if you don't like this. But everyone's familiar with Formula One racing, I think. Even if you don't like it, you know what happens. There's a car, it runs around the track very fast. Those are clearly physical cars, but in the pit lane, there's a digital version of that, a digital twin, if you like, of the physical car. It's being fed with data from the physical car. The car is bristling with sensors. In fact, the driver is also bristling with sensors to understand reaction rates and how much they're sweating and all this kind of stuff. And so in the pit lane, they actually know more about what's going on in the car and the driver than the driver does. And they're able to run that pretty much real time and then feed back information back to the driver in the physical car to go and do something. Like, for example, Hamilton, please come in next time round because we want to change your tires. And so Hamilton then says, no, I know better than the digital twin. I won't. I'll stay out. And that was the wrong decision, wasn't it? So what we see here is a very simple description of a digital twin. The essence of it. It's data going one way from the digital world into the physical world. Some kind of insights being generated, which enable better decisions. Those decisions drive interventions back in the real world, which hopefully leads to better outcomes. So I think these end up, for me, being the key words that help to describe a digital twin. I think they're part of an information value chain because more value is added by making sense of the data, leading to these better decisions. And so I think where people quite often say, oh, there's too much data, I'm drowning in data, I would argue back. You might say there's too much data, but there's too little insight. And insight has more value than the data on which it's based. And the decisions is based on the insight. And then really importantly is the feedback. So that we're not just doing this as a one-off, but once we have done our intervention, we see what the effect is. Because like I said before, we can't control the complex systems, but what we can do is understand them better. And so we can generalize it with these two blobs. And you've got the physical world, you've got the digital world, you've got data going one way, interventions going the other. And I would far rather describe digital twins than define them. I think there's a danger in defining digital twins too tightly because that becomes exclusionary and an awful lot of really good, useful things can get excluded just because some purist says, oh, that's not a proper digital twin. But I think that this helps to describe what we're really focused on. I think the digital twins are more of an approach rather than a technology because you can see that multiple different technologies can be integrated in digital twins. So you've got sensors to get data from the physical world into the digital world. You can use IoT and 5G to help get the data pumped across. Interesting to note that data can come from many different directions. And so you might want some kind of environmental or contextual information as well. So you can get kind of weather data, not just the data directly from the car. So the data can come from other directions. And then in the digital world, you've got to do all sorts of data management, particularly if data does come from multiple different sources. And then, using the buzzword bingo, AI and ML can sit inside the digital twin, helping you with some pattern spotting. I'll come back to the modeling in just a moment. And then all sorts of useful visualization technologies, AR, VR, MR, etc. Then you get your decision support. That's where you guys come in. Thank you. And then when it comes to the interventions, many different ways of doing that. You can have a human in the loop, or you can use robotics or whatever. But what I'm trying to show here is that this is not one single technology. It's a means of integrating technology for a purpose. So let's get to that word purpose. I think at the core, the thing at the heart of a digital twin that, the reason why it might have value is about making better decisions faster. If it doesn't do that, then there's probably not much point in it. And I think that purpose should drive digital twins. Generally, the purpose is something to do with some particular decisions that need to be made better or faster. When it comes to what you can have a digital twin of, it can be of individual assets or processes or systems. And so an individual asset might be a substation or, I don't know, a nuclear power plant or a bit of. Processes you can have digital twins of. So that means you can have digital twins of supply chains or digital twins of logistics, or potentially you can have digital twins of organizations or a digital twin of an economy, because those are really just different processes stuck together. And you can have digital twins of systems. So when we're talking about the physical world, it doesn't have to be a kind of you can touch it type physical world. It can also be abstract. And then inside the digital twin, there's generally three key parts. There's the managing the data part of it, hugely important because it's based on data. That's what fuels it. But then there's the modeling part, the bit that gives you the insight. And the modeling could be agent-based modeling or physics-based modeling or AI and ML, brilliant for pattern spotting, or some combination of those. It doesn't matter, because I'm going for a description that is inclusive, not exclusive. And then the visualization, because more often than not, humans want to look in and see what's happening inside the digital twin to get the understanding. But what I would caution here is not to muddle up the visualization with the model. Very often people do that. They see a nice 3D thing and they say, oh, that's the model. It's not, it's just a visualization. The model is helping you to get more insights. And crucially, the whole thing should be driven by purpose. So for example, the data refresh rate should be driven by purpose. Some digital twins will require a real-time data refresh rate, so like the millisecond. Other digital twins might not. So for example, if you've got a digital twin of a glacier, paying for a millisecond refresh rate might not be worth it, but it could be very valuable to have a digital twin of a glacier. Likewise, if you look at the fidelity of the model inside the digital twin, that should be driven by the purpose, because there's no point in paying for more fidelity than you need. The model should be good enough, not trying to be perfect, and you just kind of scrape off the top part. And then likewise, where the human fits in the loop should be driven by the purpose. And you could have the humans making the decision, or you could have the humans having thought about what the parameters of the decision are and encoding it, and then leaving it to the digital twin thereafter. So important things to think about, but a main thing here is to say there's variety. Let's not get constrained by thinking digital twin is one thing. There's many different digital twins for many different purposes, which then gets me into an even more exciting kind of place, because I think digital twins themselves are super exciting. There's no question about that. And the market, the global market for digital twins is growing at about 50% a year at the moment. This is a market that is really hot. It's going crazy. But what's even more exciting is the possibility of making connections between digital twins. So let's just go for a little example of this. If we've got a digital twin here of a train, if I had time, I'd jump into an example to show you why, like a personal example of I get fed up of getting off the train at Stevenage because the door's broken down. The door should never break down in use, because there should be a digital twin of that. There should be some acoustic sensors on the doors, some very simple AI that can spot when the acoustics is going slightly off, kind of way before a human can hear that the door's wrong, and then they should mend it. And then it doesn't break down when I'm at Stevenage. Okay, so there we've got a train. If we put that in the corner there, we've also got a digital twin of the track, because the track does all sorts of weird things in hot weather. We've got extreme weather coming along and you want to know what's going on. And then you've also got digital twins of signaling. And this is just using trains as an example. We could have used anything else. This could have been I don't know, power generation and transmission and distribution. Digital twins of different things for different purposes. And in the physical world, they're all joined up, obviously, because the train goes on the track, past the signal. What we're talking about for connected digital twins is making a connection in the digital world. So already with individual digital twins, you've got a kind of a coupling between digital and physical. It's a cyber-physical system already. But with connected digital twins, you're talking about sharing a subset of the data with another digital twin to inform it. We're not suggesting a control signal because that would create a nightmare, but giving an information signal to other digital twins to let them know information that might be useful to them. It's just another source of data from other digital twins that might be useful. And so now we've got connected digital twins. And if we apply that back to our built environment, system of systems, we can see that all around that system of systems, you can imagine lots of different digital twins for lots of different purposes. And now we're making connections between them. And the whole point of this brings me back to the bit at the top, was that can then help us to understand the systems better and intervene more effectively. So I think we've got two things going on at two different levels. For individual digital twins, it's all about making better decisions faster. If you turn that into an ecosystem and make the connections between them, then at the system level, it's understanding the system better and intervening more effectively to enable outcomes, which was the whole starting point, start with the end in mind. I hope that that makes sense. In order to make digital or enable digital twins to talk to each other, ideally they need to speak the same language. That language is a data language, so we need a semantic solution at the heart of it. I think that fundamentally that means we need a consistent approach to high quality data modeling, we need shared reference data, and we need some kind of commonality in terms of access, security, quality protocols. That's easy to say, harder to do, but it's not the only thing that needs to be done because there needs to be the work on the models and how those models might be shareable as well. It's not just about sharing data, it's about sharing other aspects to do with the ecosystem as well. Now we have had a go at this, and this is maybe a touch point with Jim around Credo. Credo was a climate resilience demonstrator that we set up as part of the National Digital Twin Programme to try and demonstrate some of these principles. And there are certain people in the audience who know an awful lot more about this than I do, Jethro. But Jethro was part of the team that delivered this and did the most fantastic job, I have to say. But what we were kind of showing was that information flow across sector boundaries could help facilitate better resilience decisions. We chose 3 different sectors: water, energy, and telecoms. There's an obvious connection between there because the water assets don't work if the energy assets don't, those don't work if the telecoms assets don't. And so we were trying to show that it would be possible to make those data connections and make better decisions. We came up with a film to make it accessible to people, and the clever people that came up with the solution did something that for me was a bit of a light bulb moment, because I like going on about systems and systems maps and showing the interconnections. But what became very clear was that the knowledge graph and the systems map were pretty much the same thing. And I rather like that because it kind of shows me that we're on the right track when we're talking about systems. Last thing for me to say is that this whole thing might sound like it's a technical problem, technical solution, and there's definitely technical stuff that we have to get our heads around. I would say that was necessary but not sufficient, because the human stuff seems to be at least as hard. In the case of Credo, it took us 6 months to get the data agreement signed, to get the data shared, and then the technical teams only had 6 months to do all the really clever stuff. That kind of illustrates that, you know, on the social side, the human and organizational factors, sorting out commercial solutions, legal solutions, regulatory solutions, ethics, training, skills, all that kind of human stuff is at least as big a problem as the technical stuff. That's it. Thank you.
Thank you very much. And just while I think about it, when we're doing Q&A after Jim's talk, the sound doesn't work particularly well unless we're close to the mic. So we will need to pass the mic this thing around the audience. It seems the sound is very good for people online as long as we're close enough to the mic. So I'm very pleased now to welcome Jim Smith.
I'll take me some time to actually get there.
That's fortunate, because it might also take me some time to share my screen because we're going to be running. Oh, Mark, can you turn screen sharing off, please? Right.
I hate seeing pictures. It looks so old. Horrible. Anyway.
Right. So far, so good. So I'm very pleased to welcome Jim Smith, who will actually speak about fairly closely related issues, but from very different perspective as a researcher in decision analysis, particularly Bayesian decision analysis. But who very much thinks about the same kind of issues that Mark has spoken about. But Jim.
Cheers. Thanks very much for inviting me to this. It already sounds really interesting. I love marketing. So what I'm going to do today is I'm going to talk a little bit about ways in which we can start thinking about this stuff mathematically. I've spent the last 25 years doing probabilistic graphical modeling. So every so often I'm going to start talking about doing that sort of stuff. In fact, it sort of fills the air, right? So and I'm also really interested in Bayesian analysis. And what I'll be trying to do here is first of all, I'll talk about Bayesian dynamic models. Then I'll talk about graphical models that have allowed us over the years to build up from fairly small scale formal analyses into much bigger ones. I'm particularly interested in dynamic environments for which energy is a dynamic environment. So I'll talk a little bit about that. And I'll be talking about how we embed scientific conjectures about what's going on within the complex environment. And the basic idea here is to try and get classes of probability models that are consistent with the way we believe systems work and interact in the way that Mark was talking about, right? So now, of course, getting this faithful to what is actually happening is tricky. And actually, when you're looking at things from an academic's point of view, you don't worry about that side of things because you just set up a set of axioms and ways in which you're going to be doing things and preposterous toy settings, and then you solve the really interesting mathematics that come out of that, right? But if you're ever trying to do this sort of stuff in reality, then and you're trying to be helpful, then somehow you've got to limp towards getting something that is as faithful as you possibly can get it to what people are telling you is happening. So one thing that's really helpful to do in doing this is these graphical models. The way things connect together and how they connect together is often some things that are associated with semantics that everybody can understand and can be comfortable. So I'll show you how we've done that, and then we'll look at some recent case studies associated with various applications. Chris has been my collaborator over the last since we met in Turin, and he's dragged me into lots and lots of different projects. He seems to get money, you know, so he's a very valuable person, but he also has an amazing set of contacts and sets of insights. And a lot of the work that we've done together is here. Did I? Woo. What's happening here? So why do we need some sort of system analysis at the moment with with energy? Well, I mean, one of the things has already been mentioned, and that's climate change. Things are really getting very different. Right? So, therefore, benchmarking on what has happened in the past is not really very helpful. We can see everything changing quickly. And so, but if we're in that sort of situation, if the environments are changing, then we've got to build in some sort of logic about what's happening, because you can't just template the new against the old. And for this, we're going to have to embed informed judgments about what's going on. And one of the things that's associated with that, which makes us uneasy as scientists, is that with all expert judgments, there are levels of uncertainty that are going into the process. And these need to be acknowledged. It's no use pretending that the uncertainty isn't there about what's going to be happening. This has to be quantified and embedded into the structure. So the point of this talk is to discuss how we can now begin to address these problems. So for energy security, we've, I think, got 4 challenges. The first is that with respect to any extreme situation, when you're talking about security of supply, you've just got those extremes, right? So you've always got much less data than you would otherwise have that's relevant to what you're looking at. So if systems are going to be breaking down, so in these sorts of settings, in high dimension, you find that you need to supplement this with some other information. This can be systematic information, it can be expert judgments, it can be usually a combination of both. So you can pull in information from other sources and talk about science associated. That's one thing. If you try and look at this sort of stuff as Chris has done, what you find is, even using the best statistical models, you tend to benchmark on the most extreme year associated with these things. And so that 1 year has an enormously influential effect on your forecast. And as a statistician, I worry about that sort of thing. Right? If you just got this 1 year, and everything seems that you're talking about in terms of forecast depends on that 1 year, really shouldn't you be at least having some sort of narrative to describe why you should be confident about that? So that's another problem. Of course, we've got 2 other challenges. One is that because of the carbon crisis, we're having new mixes of providers, and so not changing, but changing critical scenarios is a big problem. And then we've got those unexpected things, or perhaps we should have expected them, like the Russian war, which is, or the Russian special operation, stroke war. Mustn't be biased with these things. This is actually having a big impact. So what I'm going to be saying is how we're trying to use Bayesian decision analysis methods to predict analogous situations, and then talk a little bit about how we're creeping towards understanding the energy market. So this is just the Bayesian methodology. You have a class of models, and you've got an event space that you're looking at. How do you choose those? Well, coming back to the previous talk, you want to choose something that's sufficiently granular to tell the story that people are telling you about how the system is working. So you don't want it so granular that it covers everything in the world, but you want it sufficiently granular to answer that. And we also need to have the model such that any available data that looks useful can be embedded into the system. And also, we would like to include here the typical mitigating decisions that we might make to help things out. So we do that, and then we build the model. I'll say how we do that in a minute. And we've got these models and probabilities associated with them. And then we get the data, and then we find posterior distributions associated with the data. Of course, when you do this, it's what you get in the end is something which is the first few goes you do it, you find that it's all wrong. But the thing is, this is the formal what you've got here are the formal deductions from what you've been given. So when you present these back to the expert, they will say, well, that looks ridiculous. And you say, well, why does that look ridiculous? And they'll say, well, because when you do this, this happens. And you say, well, you didn't mention that when we started. So let's put that as an important element of the problem. So you move in that sort of talking to people is intrinsic to this sort of process and can take several years sometimes to actually get to something which can be called requisite and at least represents what people believe is going on in terms of the system. And of course, in these sorts of systems, when Bayesian decision analysis came out, it was in the sort of 1960s or so that it was sort of stuff. You only talked about classroom problems and one variable, And now you're talking about, some thousands of variables, sometimes hundreds and thousands of variables, and you've got joint distributions across all these things. How are you doing? So I'll show you how you can begin to look at this. And this goes back again to what Mark was saying, right? That you really do need to think about why you're doing the modeling, right? So you're trying to be as specific as you can about what things are of primary interest to you, right? And if you do that, then you can specify this class of models more appropriate, right? So we have these sort of critical features, sort of the dynamic vectors of responses that are going to be things that we're going to be interested in. And then we have our decision space. We have a utility function. Now, very often, a lot of the things I'm talking about here, those utility functions don't need to be specified early in the process, but the sort of arguments of the utility function need to be in there. Right? So we produce that. And then, right, we have now a very formal definition of what the best model is. It's the one that maximizes, that chooses the decision that maximizes the expected utility. Right? So you can start analyzing what looks like to be good decisions for that sort of conversation that we're talking about. Right? So in these sorts of situations, you provide you get explanations for what the consequences of things are, and then you've got this uneasiness that drives the diagnostics. So I've just realized that the audio of my video on my machine isn't working, and I sent an old version of my beginning version of my talk to Chris for some comments, and he's just loaded up the old version. So So it's okay. I mean, he said one of his comments was, Jim, this is ridiculously long. How can you possibly say all this in half an hour?
Should I have a quick changeover?
Yeah, why not? He desperately wants me to finish in half an hour.
I'll stop sharing briefly because very bad things can happen when you start searching through emails.
Of course, I might have sent you the old version again.
It's the email that said latest version.
Well, it was the latest version. Latest version? Stochastic. You've got to realise.
So we now have the version from the email entitled latest version.
Right. So let me. You'll see that I haven't changed it very much because I never listened to him very much. So here this is the main thing. So how do you deal with this this complex system? The basic idea here is to break it down into smaller components, a bit like a Lego model with different Lego bricks that stick into each other. And the keys that stick the brick into itself are these sort of interfaces of these things. And we've developed a theory of integrated decision support systems over the last 10 years, which enable you to pull together lots of different probabilistic models into a single unit. And we started using the overall framework was something called a dynamic Bayes net, and since that time we've produced 4 or 5 different sorts of networks where you pull these things together. And these are sorts of system diagrams, but the big thing that's nice about them is that they all support probabilistic models. So you can elicit structure from people about how things link to one another, produce a semantics of that, and then you can embellish that with quantified probability after the event. Now, the reason you do that is that a lot of the time when people are talking about how things are linked together, the way things are linked together is something which is they're happy to talk about. As soon as you start asking people for numbers and quantification, particularly probabilities and things like that, then they get things wrong. They don't know how to use the language. So you try and get that structure right. And the point is here that you can use that sort of structure to decompose the system into autonomous subsections conditional on certain inputs. So this is what we would call an integrating decision support system, right? So there are principled ways of breaking things up in this sort of way, and then you have panels of experts who curate different parts of the models that then pull together. And the point of this is that because it's coherent and consistent, these things will be, once you've bolted them together, will be able to give you faithful descriptions of the properties of the system itself. And so the probabilities propagate through the system. So that's the basic idea of doing this, and I'll show you a little bit about how that works. One of the things I would say that we've noticed is with this stuff is that if you follow the Bayesian formalism, you only need to collect these expected utility scores, and you can show that oftentimes these things only, if you're specific about what you're trying to do with the model, only need to depend on certain expectations of random variables. So you get finite lists of things that are like indices that people across different of these different components can give you, and then the mathematics gives you the algorithms. They're sort of algebraic geometry techniques that we use to actually sort this stuff out. But that's just polynomials. You just analyze these polynomials, and you get a composite picture of what happens when you pull all these things together. And in particular, you get a composite picture of how the uncertainty moves through the system. The expectation, oftentimes you've got linear things that are almost linear, just does what you expect to do in terms of the formula behind things, but the uncertainty is much more complicated. Right? But you can deal with that by just using these systems, right? And the point is that although nobody understands the whole of the system, right, and so to give you good minute relationships associated with things that are outside their domain of expertise, you can nevertheless pull these things all together, right, and taking proper account of how things broadly relate to one another, calibrate that to the data, and get your solutions of what's going on. So I'll forget about that. So you use a graph. These things are dynamic graphs, and you couple these different components together, and then what happens is you can produce one step ahead forecasts associated with what's going through the system by using ordinary probability formulae, right? And just pass through these things. Sometimes these are quite complicated formulas, but they're just standard formulae that you would use. And then you can project forward to a certain time, look at the expected utility that you would have for those outcomes, and decide give a score to what's going on, see if those things that look to be good decisions, so on and so forth, and produce something which is prescriptive about what you should do were you to believe all the things that you put into the system. Now, of course, you don't believe all those things, but because this is the logic of what comes out, were you to believe it, you can then analyze what you're doing and seeing whether this is going on. Is that time for me to give up? Is he?
No, I don't know who thinks that was.
Okay. So now, I didn't know Jethro was going to be here. Now, Jethro has drawn up these. You can see. I'm technology. I didn't actually use the internet till 1990. So technology is really something which I find a serious challenge. And I found a way to. I've used scientific words, and this is a Beamer copy of scientific words, but I don't know how to put diagrams. So I have to use a matrix function. And I draw all my diagrams by matrix. So this is quite good when you consider that is. Anyway, so here we have a sort of the type of digital twin that I've been looking at, that Credo was about and Mark was talking about. So here you have three different sorts of types of asset owners. You've got your electrician, you've got your electrical supplies, you've got your communications network, and you've got your water. And they're all sort of interested in what would happen as a response to various flooding events. So this shows how these things are interconnected, and there's under this sort of digital twin is a lot more annotation about what the links actually mean, how they happen. So how do these things work? Well, you look at this as an inferential thing, and this is a small thing compared to the major energy supply stuff, right? But it sort of makes your head burn when you realise what actually happens. First of all, we've got climate models. And what do climate models do? They have terribly complicated models that produce, and what they can only get a few of these runs every so often. They have no real proper understanding of uncertainty associated with climate, but what they can do is produce a few typical types of climate scenarios, right? That pin on to these things. So they're sort of archetypal things. If things were getting, if you're optimistic, pessimistic, or somewhere in the middle type stuff, right? So you get those forecasts coming. That's one group. Then you've got the Met Office and the weather people who will say, well, if we get these sorts of atmospheric conditions and things, and this is happening, then these are the sorts of weather events that we expect to get, and these are the types of things that happen when you have those weather events. Right? So that's another group of people. Right? Then you've got the asset owners, right, who have built pumping stations and things like that, right? And they work in certain ways, and they've been given spec. So they've tested these on various scenarios, and they know how that how it sort of works. One of the things I discovered from Krios, because I was one of the least technically able people, was that one of the major threats of flood was fire. I thought, but what happens is the water gets into the electric so that it doesn't burst down. So very long. Anyway, so actually the connection about whether an asset fails or not is actually not too tough, right? If it gets wet, it stops working. If it stays dry, it's done. It can continue to work, provided it's still going. So the point I'm making there is that there is something, you've got all these weather conditions, things associated with it, but there's a very small number of things that you really need from that. But the problem that you have is that the climate people are producing, why are they producing these climate forecasts? Well, you could say they're doing it because they need to get funding to continue doing what they're doing. So therefore, they need to produce pictures that look very convincing to politicians. Right? So that's what the climate says. What about the weather conditions? Well, if you look at the flooding models, what do flooding models do? Well, for a certain amount of money you can buy, you can see what happens in various floods. So again, it's what's driving this are the visualization associated with the flooding. So what you get out of that is not things that you would like to have, like will this particular asset actually get wet within this particular period of time, but what was the maximum depth of the flood? Right? That's what you, of course, if you ask for that, if you ask for the things that would determine whether or not that asset got wet, the Met Office could give it to you with a little effort, right? But so if you get a situation with these sorts of knock-on systems where the person who's receiving what they need asks for the specific things that they need for it, then of course you're going to get a far better model than one where people they're guessing what they need, or they're going to choose it for their own purpose. So part of the point of going through these sorts of drawing this sort of graph up is to get a feel for how these different things interact and what are critical things. One of the things that we learned when we were doing this sort of stuff was it was only when we started interviewing that we realized that after a flood, what you automatically have is a crisis center. And if you have a crisis center, they'll put the life of human life before any asset. So obviously, this is going to it throws lots of this is going to have a big impact on whether or not you can send an engineer. So all your estimates unless you build in the fact that you're going to have a price, it's you know, going to be nowhere near the reality of what's going on. So we need to ask people like this. It's not like the car example where it's bleeding obvious when things are not working, made an assumption that the tire is going to blow up and it didn't. And you've got repetitions here, you've got to rely on these judgments. So it's the comparing the judgments that you need to embed into this sort of system, right? But people give these stories, they do sound compelling, and so you can build those things in. Then what you can prove is that if that is a true Bayes net, right, then with the interface variables I give them there with letters, that's a causal Bayes net that you described there. And so there's lots of assumptions, lots of deductions that you can make through that. And the key thing here is just those random variables that are separating those things is going to be what's going to be needed. Now, teasing that out is really hard. And you know, we've got two other people working. Credo is not finished. It's not a finished project. But the point is here that if we were to be able to know what those were, even approximately, then we're going to get a long way forward. Now, these things are really nested as well, in the sense that, that if you're looking at a particular asset, then there will be another Bayes net that will be linking to that. So again, with Mark's thing, you have systems and systems. It's like plates in a Bayes net. So anyway, we've built those things. Another thing that we've looked at are carbon zero targets with some people from Newcastle. Wonderful place, Newcastle. A bit cold, but got a great football team now. The guy's not listening here. So here we have a sort of domestic heating things. The point I'm mentioning here is that, I mean, what are we doing in this sort of situation? Well, we've been brought in by North of Tyne county councils and things to develop ways in which they can choose between different heating systems to bring down their carbon emissions. So, but if you're looking at the way in which a particular user is going to be doing that, they'll need to balance lots of different things. And one of the things, you know, there's sort of environmental things, but there's also things associated with, if they've got an option, if it's going to cost a lot to the customers, then they're going to be worried about the fact that it might mean that there's not so much energy use, but it may mean they get a lot more debt of old people and things. So there's the affordability that comes out of that. And there are also things like the current cost. So there are these things that and the security of the demand as well, things that are ending up at the end of the tree contribute to what's going on. So in this sort of process, we have elicited various different attributes of utility functions. And one of the things that we found was most, I found it alarming, was the fact that the way that the local authorities were responding was they said, well, the first thing we do is we look at the government grants, right? And we'll see which ones we can get things very cheaply for if we do it, right? And then they follow that. The problem is with those government incentive schemes that they change every year or two, right? So in terms of consistency of choice, it's a complete mess. Anyway. So, and within that, we would look at particular assets, and each one of those assets, again, has a particular Bayes net structure on which we can manage on. So, I just finished with talking a little bit about what we've been doing most recently in terms of energy. It's one of the things that I'm sure Chris will talk to this, but it's something that he talks about a lot. But in energy, unlike in that situation that I just described, the utility function is often not seen as a multi-attribute utility. It's instead, everything is reduced to money. Money is monetized. And although you can do that really quite effectively for some problems, we would argue that this is not a good place to just try and reduce everything to a cost equivalent. It's much more sensible to try and keep these separate. So that's second thing is that when you're making decisions, rather than you just using various expected measures, expectation measures, it's really helpful if you at least try and admit that you're sort of a risk averse, what's going on, and use some sort of value at risk, C-bar type thing. And you can show that if you are to do that and you're being led by those sorts of decisions, then the sorts of decisions that you make are much more believable and acceptable and faithful to the way people think about these things than if you just focus on the expectations. One of the things that we did find was that, I was mentioning here that in the climate stuff, that we're in this situation where things are getting a lot more extreme. And there are sorts of extremes that you've sort of seen before, but are just happening more often. And then there are extremes that are just things that you've never actually experienced. As the planet warms up, so those atypical extremes start to multiply, right? And so one of the things that we found is that it's a very good idea to separate those two different settings from one another. So why did it do that? So these are the sorts of dynamic Bayes nets that we're building. You get different shapes for demand and supply. One of the things that you find is that a lot of the software that uses this stuff, when things are big continuous variables, tends to be Gaussian, and you really, or numerical. So you really, the Gaussian stuff really isn't going to fit because streams aren't Gaussian, and the numerical stuff is flat, right? So it's really difficult to do work on this. So there's still lots of difficulties associated with dealing with systems analysis and intrinsic uncertainty. One is, can you conceptualize risks in a systematic way? One of the things that's associated with these systematic methods is that, of course, you can only be systematic about things that you can know you know about. If things are unexpected, the unknown, then you're going to be your unknown knowns. You're going to be a bit stuffed. So there's a challenge to manage technological uncertainty. And actually take things beyond 2000. So, however, what I would say here is this sort of subjective Bayesian methodology where you embed expert judgments to capture the uncertainty is really essential for these big problems. I'm sure that there will be other ways of doing things, but in terms of 50 years of theory about when these things go right and things go wrong, the Bayesian methodology is a very good one to do that sort of thing. That if you fix to the strategic questions associated with what's going on, then if you build these IDSS systems up, then actually they're turning out to be feasible. And the reason they can be turned out to be feasible is that they can be characterized by just a finite set of indices of expectations of functions of indices. But on the other hand, we've got to acknowledge that there are deep uncertainties associated with these things. Two things. Think about the decisions that you might be wanting to make, and think about, in any modeling, the agility of the system to be able to do something half decent, even when things turn out to be in a way that you think could never happen. That's me. Cheers.
Right, thank you very much. So I'll just take this off. Am I taking this off screen sharing? No, I'll take it off screen sharing so that I can see what's coming in on the chat. So any questions here from in the room or from in the audience online? And just to recap, I'll have to pass this around, otherwise people outside, people watching at home or in the office won't be able to hear us.
Hi, I work on energy systems and weather modeling, and so I wonder what's the kind of proper mathematical answer to the over-optimization problem, right? So let's say you have an extreme that collapses some part of your electrical system, and you look into the history and you look at, this is like 1 in the 40 years event that caused this. But the intuition tells me that this extreme event is never going to happen again because it's so improbable that this specific, like there's going to be another very extreme event that will collapse out the grid. But if we then, I don't know, reinforce the grid to deal with that extreme event, we're actually missing the point because that one is as rare as, and is never going to, the sequence of events that cause the collapse is never going to happen exactly. So how do you mathematically describe that?
First of all, that's an excellent question, right? But the thing is, if you've got a coarse model, right, then hopefully what you're saying within the model is that there's some sort of smoothing across what's going on. So you're not only forecasting, again, exactly the same instance, right, that was going on, but you're learning from that about all similar instances that were like that. So if you build up a probabilistic model, of course, you know, there's a lot of conjecture in that, but if you've got some idea of why things happened and why things were bad and, you know, why certain bits of machinery got flooded or whatever, right? You can quite plausibly work out those sort of what-if scenarios around that other thing. So it isn't like a repetition of that type of thing that you're sort of interested in. So those things you can sort of, statisticians will be with careful building of what corresponds to being a similar situation, you can then build up reasonable forecasts of what's going on. And those things like that or similar to that could be expected to happen. And now when things are changing, more often, right? So you begin to sort of, you can start predicting what's going on. We're using that flooding model for strategic analyses, and we're sort of saying, well, what will happen in another 10 years or so if we were to rebuild the structure of the assets so that they're a little bit more robust, right? And so we can with some sort of a credibility say, well, we're going to get something that's like this, and this will have this type of effect, and so. What you don't have, of course, is any data on things that are completely different from anything else you've seen, unless you import that from some other country. And that's a real issue. problem.
So, yeah, just to build on the same kind of point, I think if you have seen some specific instance of an unlikely event and can see what happens with that in that place, as you say, it's very unlikely that the same thing will happen in exactly that same place. There's no point to strengthen just that same place. However, if you've now identified what happens when that type of thing occurs, then you can look across the rest of the system and to see where in the rest of the system is vulnerable to that type of thing happening, and then identify which part of the system you therefore need to strengthen up. So I think it's a kind of a slightly different approach, but it's taking a specific example and then applying it across the system to strengthen the whole system rather than just the little bit of the system.
So there is, taking that point, yeah,
The fact that you can say that different parts of the system are similar and therefore
respond similarly. And the point that I was making, that different sorts of environmental events would happen which were similar, that would have a similar effect on a particular aspect.
But I think there is also, some extent to which degree of challenge with this vary between cases. So, for instance, if you're looking at national supply demand balance on electricity, you've got some significant degree of sort of homogeneity between events there, in that you're dealing to some reasonable extent with a single number of balance of available supply versus demand, or single time series, whereas it becomes much more complicated. For instance, if you're looking at storm events and what assets they damage. Anyway, I think we've got a couple more points over here. So,
Do you want to go first?
John, thanks. It's really very fascinating. This question may be a little more for Mark. So I'm always, when I think about the climate dynamic and challenge that we're facing, I think, of course, for Jim too, but I come to this kind of conundrum that I don't know how to answer, which is around national security. And so, the question, I'm more of an economist, statistician kind of background. When you think about the amount of energy it takes in order to produce goods, right? And you start thinking about solutions that we are looking to implement, so wind, solar, that either have to have some kind of redundant natural, gas or coal backup system in order to get the reliability you need, even though you don't use those very often, so you do get your carbon footprint down. But the cost structure goes up dramatically. And so kind of the rough question is something along the lines of, kind of fits into the German problem, like you don't want to give away core capacities to your enemy potentially, right? You don't also want to make it so that it costs you twice as much to build a tank as it costs China to build a tank. As we think about the next 20, 30, 50 years and the geopolitical struggles that are likely to unfold, but the West insists on having an energy cost structure that's twice what China or Russia will insist on. That's going to put us at an economic disadvantage, and we're going to have to make trade-offs there: national security, healthcare, just standards of living, et cetera, et cetera. So I'm very curious. I rarely hear someone, people wrestle with. I'm all for us making the world better, but I don't see the Chinese really being on the bandwagon in a practical, pragmatic way. So maybe this is beyond the scope.
I'm sorry. I've just had a request from online for something I should have said anyway. When people ask questions, could you just say name and institution?
Oh, sure. Yeah. So my name is John Lichty. I'm at Penn State University. I'm on sabbatical right now at Churchill College.
So just to give you on.
Well, I want to say something. I think this is a very good point. Again, it's a big decision to be made. It's a political decision. Right?
I think one of the things that you can do as a scientist is to try and be as trying to ensure that things are consistent as possible, so that if you're following a particular trade-off, that you find the optimal way of actually getting to that trade-off. But those trade-offs have to be made by the people that run our country.
Yeah, absolutely. And that's why we have the problem. Because they don't, yeah, anyway.
Yeah, so I think that we do absolutely have to wrestle with those kind of issues. I mean, to my mind, it's still about outcomes and about the systems. We've just been modelling slightly different outcomes and slightly different systems. So I think that when it comes to the type of outcomes which are relevant at a national level in relation to climate change and the type of threats which might come up, then we can kind of see that you might get to a place where you've kind of got to come down Maslow's triangle a bit and not just be thinking we're at the top trying to have this kind of self-realization, whatever it is. But maybe we're talking more at the bottom of the triangle around survivability outcomes and what is going to enable people to still stay where they are and not become migrants. And you're looking at some pretty serious things. And what is the minimum that people will need to have in order to stay in a place and for it to be livable. But that kind of modelling, I think, then needs to take into account also what's happening in other countries, because if their situation becomes unlivable, then they will become migrants and come pouring across the border to where it's more livable. But I think the issue is exactly the same. It's about understanding the system and trying to drive the outcomes. It might just be, though, that if we get into those kind of really unpleasant kind of places that climate change might drive for us, that we just got to imagine a lower level beneficial outcomes.
Just building on that, one of the things that is, of course, very important is there is a narrative within the West that if we do this, we take the lead, then everybody will follow. So there is a sort of, so one needs to model that, embed what the likelihood is, what the likely response is going to be when you do certain things, and you could take an optimistic or pessimistic view to that. But given that side of things, you can then work out what the total effect on the carbon emissions is going to be by you taking a certain action. Right? So the reason I'm mentioning that is that's another part of the system, right? That you could model systematic to take it, but I don't think many people do. I don't think you'd see that happening.
Okay, coming up to 5:30 when we were scheduled to finish, so I think we can run over a little bit, but if people need to leave, don't feel you're being impolite. I'm just going to come back here. We actually had a specific request for your name. If there's someone online who's interested in energy security, was interested in the question.
Yeah, I'm a Peter Dolezal, PD 423 at cam.uk, and I work at Computer Lab on modeling energy.
Thanks. So we've got one from Lars, and then I'll maybe take the questions from Lars and Ian together, and then we'll then pass them on to Jim and Mark.
Hi, I'm Shiva, University of Edinburgh. So I was wondering, also in context of with the over-optimization question, both in data collection, so more towards Mark's talk, as towards integration, towards Jim talk, how you see the role of sort of, let's call them high fidelity physical models, so very good physical models, say a PDE-based model of an energy system. How would they fit in your framework? And how do you actually think, because my experience with projects was, it's very easy that if you separate the data collection aspect, which you had separated out, Mark, on your slide, from the model development aspect, that essentially you always, if you think of the models in a sort of hierarchy, you always drop down to almost the bottom because you're missing something. You have almost the right set of data to model it in a very sort of high, let's call it high fidelity way, but you're missing something that essentially makes your model almost worthless. And so you always end up saying, well, our energy grid is just a graph, which is when we can track whether it's still connected, but we can't do any, say, if you think electricity, we can't do power flow. So how do you think, sort of in both of your talks, how could we integrate these physical models that are well tested, well known, and people trust them? How would they work in there? Thanks.
Yeah, Ian Steffel from Imperial College London. Thank you both for your talks. I think, Mark, one of the messages I took from your talk was that really what you want to achieve is better decisions that deliver better outcomes. And perhaps related to the previous question, although on a smaller scale, I'm wondering how can you deal with issues where there is no consensus on what the outcome should be? So I'm thinking, for example, of low traffic neighbourhoods, which is, I think, an issue going throughout Oxford and all throughout London. One outcome that is desirable is cleaner air. Another outcome that's desirable is short commute times, and the two are mutually exclusive. And we've now got to the point where old people are being run over because they are, trying to enforce a low traffic neighbourhood. I'm guessing people running each other over is not the kind of outcome that any of these digital twin models would ever be able to predict. So what can we do with these kind of humans being very different from what you would imagine types of problems?
Right, so who like keep up on that? So great questions both. Just to pick up on yours first, Lars, I think that the idea of this kind of inconsistent fidelity is a really important one to grapple with, because I can see that it may well be possible, in fact likely, that you'd need to have a pretty high fidelity model of a particular asset in order to make the type of decision which is relevant for that asset. And in my example of the train, you would not want to have the detail of a train's door in a model of the overall railway network. That level would not be appropriate. So what I imagine is that for the lower level digital twins, which are focused on making better decisions for individual assets, there'll be a high fidelity model for that purpose. But then there'll be something about that particular model, that interaction outside the physical system, that will be relevant to a higher level model. Not all of the data, but just a subset of that data. And I think that what would be useful is to be able to get whatever is relevant to feed across to the higher level model, not the whole thing. So you don't overburden the system or network level model with all the detail of an asset level model. So if we're imagining some nested models, the higher up you go until you kind of get to the highest level one, which might be of the whole economy, you don't need all of that asset detail. So the clever thing will be knowing what subset of data you feed up.
Yeah, can I just for consistency with questions? So obviously, if you've got a probabilistic model associated with those things, this is essentially a marginalization operation. So if you can do that, and you can make sure that everything is consistent with everything else, and that things are not working independently of each other, but are informing each other. One thing I would say, well, two things I'll say. I've worked with physicists for many years in nuclear industry, and using increasingly more complicated PDEs to forecast atmospheric dispersal. And they are awful in terms of their forecasting. The more complicated they get, when you actually try and emulate it against an experiment. I remember one thing where we emulated this plume using one of their models. This was in Denmark, and we had all these different PDEs, and first of all, they wouldn't work unless you had sufficiently quiet atmospheric conditions. So we had to wait 2 weeks, and then we let these things off, and they all predicted the plume was going off to the left. And what happened was the plume went up in the air and then came straight back down on the chimney, right? Now we still maintain the funding by doing a comparative analysis across the different things and not saying that, but right, it did make me feel that you know the actual fidelity of these models in that context, when you're talking about atmospheric things, are, you know, if it's below or above the advection layer, you get completely different answers, and you get these sorts of things that are not predicted. So I don't believe those. And finally, if things are getting more complicated and having to do with the uncertainty handling, then emulations is an obvious way forward. Using the physical models to give you your simulation analogs and then emulating around.
Yeah, I think one of the points to make there is when you're dealing with very complex systems, I mean, there's a general point that as models grow more complex, then typically people do that in order to learn more about very complex systems. But because the model becomes more flexible and with reasonable inputs, you can make it do almost anything. As the model becomes more complex, there's a sense in which you degrade your ability to understand what the model is telling you about the world. And obviously, I mean, there are some, there are different cases for that. So, for instance, if you have something like an electricity network where you have pretty well-defined physical governing equations, then if you have if you have precise data on what's driving it, then you can make precise predictions or pretty precise predictions. I mean, I guess GINS is a good example of where you can have all the fidelity you like in your in your physical atmospheric model, but if you don't have certain measurements of atmospheric conditions which you're not going to have, then it's
and there is also another thing that we can consider is, and this is something that economists know, right? If you're doing a macro, the things that matter, the covariates that matter in a macro setting are very different from the micro, because what's really important for getting forecasts right at the small level can be very different in terms when you're looking at aggregates. Small correlations associated with things when you aggregate things up have an enormous effect on the aggregate, right? Which are not on the individual. So there's lots of helpful news associated with how you do it.
And I think that there is then a link connection into Ian's question. So again, quite briefly on that one, I think that this thing about defining what the right outcomes are is clearly something that needs input from multiple stakeholders. It's not okay just to have one person say this is the outcome we want. And so having the kind of the clean airists versus the short drive to workists need to kind of work out how to get to what the right outcome would be at that local level. I think that should be a democratic process. You know, I think it's actually intensely a democratic thing to discuss what outcomes we want to share to get together. But the thing I would just want to add into it again is this notion of layers, because there would be that local level at which you would have that kind of discussion between those two groups. But then it might be different when you look at the city level or the national level. And I think that it becomes important, therefore, not just to have this kind of modeling that we discussed, being able to have these layers and have information fed up, but also the outcomes and potentially also the decisions which are being made. So at each of those levels, it seems to me that there needs to be this kind of alignment. I discussed it briefly when I was talking about outcomes, going all the way from the local outcomes to the kind of the SDGs. I think that outcome thinking, that outline, I need to get my words right, that kind of alignment of thinking around outcomes is the same as this alignment around the models, which was the answer to the previous question, and the alignment around decisions and how you get to know what kind of outcomes you want. Because it could easily be that if you came to a local decision about what was best, let's just say that the short journey to work is one. When you're looking at a city level, that actually it becomes more important for air quality. And at a national level, you're trying to reduce the number of journeys. So actually, that local decision on outcomes is wrong after all, and it should be informed by what is relevant at a city and a national level, not just an isolated local one. So it's a long way around me saying that these are actually all connected, and what we should intend to do is aim for the alignment rather than just think that these are completely separate things. And I think if I can just make one more point on this, very often when we talk about silos, we kind of almost imagine them as horizontal silos, like there's a silo between energy and transport and water. It's they're next to each other. I think that there's also silos which are kind of stacked above each other, kind of silos between the assets and the networks and the systems and the economy. Really what we should be doing if we're doing systems thinking is breaking all of those silos, getting information flows, across the way, but also up the way, if that makes sense.
Jim.
Well, I mean, that was very good and full answer. One of the things that I make a very pedestrian point that if you, with that sort of problem, if you try and break the thing down into a single number, right, you've lost the whole point of what's going on. Right? So it really is important to keep these attributes separate late on, so that they can be discussed and a decision can be made, and that you don't obfuscate the problem by pushing down and say this has got a higher score than that because of this sort of cost frame.
Yeah, I think Jim's made the point that I was essentially going to make, and I think sometimes this one view I have is that sometimes these points about remembering that you can't always reduce everything to the same numerical scale sometimes gets a bit lost. I mean, certainly in research where there are providing a visualization and partly leaving it to providing visualization of what would happen on these different metrics for different decisions is and to a significant extent leaving it to the decision maker to decide how these things balance off. It isn't always something on which you can write fancy algorithms, or you need to write fancy algorithms or kind of things that get us kudos in academic literature. We often, but I think very often remembering what starts off as cash flow, what doesn't, remembering that money, even with discounting, money now is not quite the same thing as money in the future, and presenting information in a way that recognises that there are good pragmatic steps where we don't need to wait for a big research project to improve how this fits together. I think we should break for lunch now. Otherwise, I'll be violating my first rule of event organisation, which is allow an hour for lunch. There's at least one option, which is the Centre for Mathematical Sciences Cafe, which is the other end of this sort of grassy plaza, where all the pavilions very nicely are marching towards that. That's sandwiches, soup, kind of snack lunch type hot food. If anyone was interested, I'm not sure what questions the Churchillians here can anyone just go and pay at the buttery, or is it something where you need some form of card? But there is that other option if you want to put a full meal, and if you do, I or one of the or a few of the others can point you in the right direction. But for myself, I'll actually be going to the Mathematical Sciences Cafe because someone so someone tried to call me during this session, and I'll probably have to duck out at some point and call him back at lunchtime. But anyway, I'd just like to thank everyone for being here and for your attention and the discussion, and we'll reconvene at quarter to two. Where Janusz will take over chairing, and hopefully, if he's uploading any slides, we'll do a better job of uploading slides than I did. Anyway, thanks again. And should we just thank Jim and Mark again?